Right now, scientists tracking the sun and the invisible shield surrounding this planet are dealing with a finding that quietly rewrites 4 decades of assumptions about how bad a solar storm can actually get. For as long as space weather forecasters have been keeping detailed records, there has been a comforting idea sitting underneath every worst-case model built to protect power grids, satellites, and communication networks: the belief that Earth's magnetic field has a ceiling, a point past which even the most violent eruption from the sun simply cannot push our planet's response any further. That ceiling has just been shown to be an illusion, a statistical mirage buried inside the very data forecasters have relied on since the 1990s. And the timing of this discovery could not be more significant, because it lands during a stretch of the solar cycle that history shows is exactly when the most extreme storms tend to strike, with an actively unstable sunspot region facing Earth right now and forecasters watching the next several days with real, justified attention. Today we are breaking down exactly what this new research found, why the old ceiling turned out to be fake, what that means for the actual scale of danger the next major storm could bring, and why the specific week we are in right now matters more than most people currently realize. No exaggeration, no doomsday theatrics, just the science, the numbers, and what it actually means for the systems that quietly run modern life. If you have ever seen the aurora somewhere you never expected to, or if you have followed solar storm forecasts before, drop a comment and tell us where you were and what you saw, because these observations from ordinary people scattered across the globe genuinely help researchers piece together how far these effects actually reach. And if you want to stay ahead of space weather developments like this one as they unfold, go ahead and subscribe now, because this is a story that is very much still being written in real time. Let's start with what a geomagnetic storm actually is, because understanding the mechanics here makes it much easier to understand why this new finding matters so much. The sun is constantly releasing a stream of charged particles called the solar wind, and every so often a much more violent eruption called a coronal mass ejection, or CME, blasts an enormous cloud of magnetized plasma directly out into space. When one of these eruptions happens to be aimed at Earth, that cloud of plasma takes anywhere from 1 to 3 days to cross the roughly 93 million miles separating us from the sun, and when it finally arrives, it slams into Earth's magnetosphere, the protective magnetic bubble generated deep inside our planet's molten core that shields us from the worst of what space can throw at us. That collision compresses the magnetosphere and, depending on the orientation of the incoming magnetic field, can trigger a cascade of electric currents that flow through the upper atmosphere and down into the ionosphere. Those currents are the actual mechanism of damage in a severe geomagnetic storm. They are what disrupts GPS signals, degrades high-frequency radio communication, threatens the health of satellites in orbit, and, in the worst cases, induces dangerous surges of current in the very same high-voltage transformers that keep continent-spanning power grids running. For decades, the way scientists measured the strength of this interaction was by tracking a value called the solar wind electric field, essentially a measurement of how strongly the incoming plasma is driving currents into Earth's magnetic environment. And for just as many decades, when researchers plotted that driving strength against the resulting geomagnetic response, the data appeared to flatten out at the extreme end. No matter how much stronger the incoming solar wind got, the geomagnetic response seemed to stop climbing past a certain point. Physicists gave this apparent flattening a name: saturation. And once you name a phenomenon, once you give it a label and build models around it, it tends to become an accepted piece of the underlying architecture that engineers, grid operators, and satellite designers plan their worst-case scenarios around. Here is where the new research, published in the journal Nature by a team led by Nitin Sivadas, alongside co-authors including David Siebeck and researchers from institutions like Lancaster University, completely upends that architecture. The team went back through decades of solar wind measurements taken at a location called L1, a gravitationally stable point roughly 1 million miles from Earth, directly in the path of the incoming solar wind, where spacecraft have been stationed since the 1990s, specifically to give forecasters advance warning of incoming space weather. And what they found is that the apparent ceiling was never a real physical limit at all. It was a statistical error, specifically a phenomenon called regression to the mean, quietly distorting the data the entire time. Here's the mechanism in plain terms, because it is genuinely one of the more elegant explanations to come out of space weather research in years. Measuring the solar wind's driving strength from a single spacecraft parked at L1 involves real uncertainty, because that one spacecraft is only sampling a small slice of a much larger, turbulent stream of plasma. During the most extreme events, an unusually high reading captured at that single point is statistically more likely to be a brief, localized spike rather than a perfectly accurate representation of the broader wind actually approaching Earth. When researchers paired those inflated extreme readings with the real, slightly weaker response actually observed in Earth's magnetic field, and then averaged large numbers of these events together the way standard analysis techniques require, the mismatch between the inflated input and the more modest output bent the top of the response curve flat. It manufactured the appearance of a ceiling that never actually existed in the underlying physics, purely as a side effect of how the averaging was done. And critically, the researchers found that this measurement mismatch runs to at least 30% of the driving strength and actually widens as the storm gets more extreme, which is exactly why the illusion of a hard ceiling looked strongest during the rarest, most violent events on record, the very events where accurately understanding the true risk matters most. Once the team corrected for that statistical distortion, the ceiling simply disappeared. The corrected relationship between solar wind strength and Earth's magnetic response keeps climbing in a clean, direct line, with no evidence of any true physical limit anywhere in the dataset. At the extreme driving strengths seen only in the rarest storms, roughly 25 millivolts per meter, the corrected response reaches double what the old, saturated model would have predicted. Co-author Maria Wallach from Lancaster University explained the practical stakes of this finding by pointing out that Earth's magnetic field does an excellent job protecting us against most space weather effects, meaning the vast majority of geomagnetic activity shows up as nothing more dramatic than a glitch here or a beautiful aurora display there. But she was direct in noting that there are extreme cases, and this research specifically targets those extreme cases, the ones sitting at the very tail end of the probability curve, where the consequences for modern infrastructure would be most severe. If confirmed by further observation, and the authors themselves are careful to note that genuinely extreme storms remain rare, which naturally limits how much data exists to test this against, the implication is that risk estimates for what scientists call once-in-a-thousand-year geomagnetic events have likely been built on a foundation that quietly underestimated the true danger for the entire modern era of space weather forecasting. To understand why doubling that worst-case estimate actually matters in practical terms, it helps to look at what happens when a severe geomagnetic storm interacts with the specific infrastructure modern society depends on. A severe storm does its damage primarily through electric current, not through light or heat, and the component most at risk sits inside the high-voltage transformers that form the backbone of long-distance electrical transmission. When a powerful geomagnetically induced current flows through one of these transformers, it can push the transformer's magnetic core into a state called saturation, a completely different use of that word than the statistical saturation we just walked through. And this physical saturation causes the transformer to overheat, draw excessive reactive power, and, in the most severe cases, suffer permanent physical damage that can take the unit offline for months, while a replacement is manufactured and shipped, since these specialized transformers are not something utilities typically keep sitting in a warehouse ready to swap in overnight. The historical benchmark for just how bad this can get remains the Carrington Event of September 1859, the strongest geomagnetic storm ever recorded, named after the British astronomer who documented the solar flare that triggered it. That storm was powerful enough to light up auroras as far south as the Caribbean, and induced enough current into the telegraph wires of the era that operators reported sparks visibly jumping from their equipment, with some lines reportedly continuing to transmit messages even after operators had disconnected their batteries entirely. Powered purely by the current the storm itself was inducing into the wires. A storm of that magnitude striking the modern world would meet an infrastructure landscape that simply did not exist in 1859, a continent-spanning network of thousands of interconnected high-voltage transformers, none of which were engineered with anything like a Carrington scale event in mind when the original saturation ceiling was assumed to cap the worst-case scenario planners needed to prepare for. This is not a purely historical or theoretical concern either, because the last two solar cycles have both produced storms serious enough to serve as real-world stress tests. In May of 2024, the strongest geomagnetic storm in more than 2 decades struck Earth, driven by a series of powerful coronal mass ejections launching from an unusually large and magnetically complex sunspot region. That event pushed the disturbance storm time index, the standard scientific measurement of storm severity, down to a peak of negative 412 nanoteslas, with some readings suggesting it may have reached as low as negative 518, making it the most intense storm since the historic Halloween storms of 2003. It produced auroras visible across much of the United States and Europe, far south of where they normally appear, while simultaneously causing intermittent disruptions to high-frequency radio communications, GPS-guided agricultural and industrial equipment, and select satellite operations. And yet, even at that intensity, the May 2024 storm was still considerably less powerful than the Carrington event, let alone the even more extreme scenarios this new research suggests may now be physically possible once you remove the artificial ceiling from the modeling. Which brings us directly to why the current window of time carries genuine significance rather than being just another routine solar update. We are currently sitting inside the declining phase of solar cycle 25, the 11-year cycle during which the sun's magnetic activity rises to a peak and then gradually winds back down before the next cycle begins. According to NOAA's own tracking data, this particular cycle reached its peak sunspot activity back in the summer of 2024, and the monthly sunspot number has been trending generally downward since, with the most recent figure for July coming in at 78. 1, down from June's reading of 94. 4, on the surface, a declining sunspot count might sound like it should mean declining risk, and in terms of the sheer frequency of solar flares and eruptions, that is broadly true. But here is the detail that space weather historians consistently point back to. And it is the exact reason forecasters do not relax their guard simply because the overall sunspot count is falling. Some of the most extreme geomagnetic storms in the historical record have actually occurred during the declining phase of a solar cycle rather than at its peak. The mechanism behind this is still an active area of research, but the leading explanation involves the specific type of solar structures that tend to dominate during a cycle's later years, including large coronal holes and long-lived magnetically complex active regions that can produce isolated but exceptionally powerful eruptions, even as the overall pace of activity slows down. In other words, a quieter sun on average does not mean a safer sun during any individual week, and the declining phase has a track record of producing exactly the kind of outlier events that this new research suggests may now carry twice the impact previously assumed. Right now, as of the most recent solar monitoring available, the sun's Earth-facing disk includes an active sunspot region designated AR4498, which observers using specialized hydrogen alpha filters have confirmed carries what solar physicists call a beta-delta magnetic classification. That classification matters enormously to forecasters because it describes a sunspot group where regions of opposite magnetic polarity sit crowded unusually close together within a single complex structure. That kind of tightly packed, conflicting magnetic geometry is precisely the configuration most associated with instability. And instability in a sunspot's magnetic field is what ultimately gets released as a solar flare when the built-up magnetic tension finally snaps and reconnects. A beta-delta classification specifically signals that a region is harboring enough stored magnetic energy to produce a significant M-class solar flare. And under the right circumstances, active regions with this kind of complexity have historically been capable of producing the far more powerful X-class flares as well, the strongest category the current classification scale recognizes. This is not a hypothetical concern about some future active region that might eventually rotate into view. This is the actual current magnetic geometry sitting on the Earth-facing side of the Sun as this window of heightened attention unfolds. And it is exactly the kind of structure that forecasters at NOAA's Space Weather Prediction Center watch multiple times a day, specifically because regions like it are the ones most likely to produce the kind of eruption capable of triggering a serious geomagnetic response once any resulting plasma cloud makes its 1 to 3 day journey across the intervening space to reach us. There's also a more recent, very concrete example from just weeks ago that illustrates exactly why forecasters have become increasingly cautious about how confidently they can predict a storm's final strength purely from pre-arrival modeling. In early July, a geomagnetic storm arrived at Earth and escalated to G3 strength on the standard geomagnetic storm scale, a level classified as strong. And critically, it arrived 2 full intensity levels above what NOAA's own pre-arrival forecast had projected. The reason traces back to a phenomenon researchers call a cannibal CME, which happens when a faster-moving cloud of solar plasma catches up to and merges with a slower cloud still in transit ahead of it. When that merger occurs, the two structures combine into what scientists term complex ejecta, a single combined cloud carrying more cumulative magnetic energy than either individual eruption would have delivered on its own. And crucially, the exact strength and orientation of that merged structure is extremely difficult to predict in advance using current forecasting tools. The historical record shows that the very worst space weather events in recorded history have often involved exactly this kind of multiple, successive eruption merging together, including the original Carrington Event itself, which involved several distinct eruptions and produced auroras visible at unusually low latitudes for 4 consecutive nights, rather than the single-night events more typical of an isolated storm. At the time of that early July cannibal CME, active region AR4494 was displaying the same beta-delta magnetic complexity, now being tracked in the current sunspot activity, while a second region nearby continued growing and retained what forecasters described as many days of ongoing geo-effective potential, meaning its magnetic orientation remained capable of producing Earth-directed activity for an extended stretch rather than a single isolated event. Put all of these pieces together, and the reason the current stretch of days carries real weight becomes clear. You have a newly corrected scientific understanding, showing that the worst-case ceiling scientists have used to plan grid and satellite risk for the past 30 years was never actually real, with the true worst case potentially running twice as severe as previously modeled. You have a solar cycle currently sitting in its declining phase, a period with a well-documented historical tendency to produce outlier extreme storms, even as average activity trends downward. You have an active, magnetically unstable sunspot region on the Earth-facing side of the Sun right now, carrying the specific beta-delta classification associated with significant flare potential. And you have a demonstrated recent precedent from earlier this same summer showing that when multiple eruptions merge into complex ejecta, the resulting storm can blow directly past pre-arrival forecasts by multiple full intensity levels, with very little additional warning once that merger actually happens. None of these four factors on their own would necessarily justify heightened attention. Together, layered on top of each other during the same narrow window, they explain precisely why space weather forecasters are treating the current stretch with a level of vigilance that goes beyond the routine daily monitoring that defines most weeks of the solar cycle. It is worth being clear about what this actually means for ordinary people going about their daily lives, because the honest answer sits somewhere between complete indifference and genuine concern, and getting that balance right matters. For the vast majority of people, even a severe geomagnetic storm produces effects that are, at worst, a mild inconvenience. A temporarily degraded GPS signal, some static on high-frequency radio bands, or, more excitingly, a rare chance to see the aurora borealis at latitudes far south of where it normally appears, turning what would otherwise be an invisible piece of space physics into a genuinely beautiful nighttime spectacle, visible to anyone who steps outside and looks up. The far more serious potential consequences, the kind directly tied to this new doubled risk estimate, concern the infrastructure operators and engineers responsible for power grids, satellite constellations, aviation systems that rely on precise GPS positioning, and the increasingly interconnected digital backbone that underpins nearly everything else in modern life. Utility operators across North America and Europe already incorporate space weather alerts into their operational planning, and severe geomagnetic storm warnings can prompt temporary precautionary measures, including adjusting transformer loads or bringing additional monitoring online during a storm's peak window, specifically to reduce the risk of the kind of core saturation that leads to permanent equipment damage. Satellite operators similarly track these forecasts closely, since increased atmospheric drag during a strong geomagnetic storm can measurably affect the orbits of satellites in low Earth orbit, a real operational concern for the thousands of small satellites that now populate that region of space in numbers that simply did not exist even a decade ago. Some individuals also report feeling physically different during periods of elevated geomagnetic activity, describing symptoms like headaches, fatigue, or general discomfort. And while researchers studying this connection are careful to describe it as a possible rather than confirmed effect, a body of statistical research stretching back nearly a century has repeatedly found correlations between geomagnetic activity levels and changes in measures like blood pressure, sleep quality, and cardiovascular events among people who describe themselves as weather sensitive. Proposed mechanisms researchers have explored include effects on melatonin and cortisol production, subtle changes in blood viscosity, and the behavior of certain proteins that appear to respond to magnetic field fluctuations, though none of these mechanisms have been definitively proven as the underlying cause. The practical, reasonable takeaway from that body of research is not alarm, but simple awareness. If someone notices their own well-being shifting on days with elevated solar or geomagnetic activity, tracking that pattern alongside publicly available space weather forecasts is a safe, low-effort way to see whether a genuine personal correlation exists without needing to treat every storm warning as a cause for concern in itself. Looking forward, the most important thing to understand about this newly corrected science is that it does not mean a catastrophic storm is imminent, and the researchers behind the study have been careful and consistent in making that distinction clear. What it means is that the tools used to estimate the plausible worst case, the numbers that insurance analysts, grid engineers, and government risk assessments have leaned on for decades when asking how bad the rarest possible event could get, were quietly built on a foundation that underestimated that worst case by as much as half. That is a meaningfully different kind of finding than a prediction of imminent disaster. It is closer to discovering that a bridge rated to withstand a certain maximum load was actually tested using flawed instruments, and the true safety margin engineers believed they had built in was never as large as everyone assumed. The bridge is not about to collapse. But every future decision about reinforcing it, ensuring it, or planning around its failure now needs to be made using corrected numbers rather than the comfortable, understated ones everyone had been working from for the past 30 years. Space weather agencies around the world are now working through exactly what this correction means for their own long-term risk models, a process that will likely take considerable time Given how deeply the old saturation assumption was embedded across satellite design standards, grid resilience planning, and international space weather risk assessments built up over decades. In the meantime, the sun continues doing what it has always done, cycling through periods of relative calm and periods of genuine volatility, indifferent to how confidently or how poorly the models tracking it have managed to capture its true extremes. If you found this breakdown useful, take a moment to like the video and share it with anyone who works in infrastructure, aviation, or satellite operations, because understanding that this ceiling was never real is exactly the kind of information that shapes how seriously the next severe storm warning gets taken. And make sure you are subscribed, because between an active, magnetically complex sunspot region facing Earth right now and a corrected scientific understanding of just how extreme these storms can genuinely get, this is very likely a story we will be returning to again before this particular window closes. It is worth spending a bit more time on how forecasters actually watch for these events day to day, because the process is far more methodical than simply waiting to see what shows up in the sky. NOAA's Space Weather Prediction Center, working jointly with the U.S. Air Force, issues daily solar and geophysical activity reports that track every numbered sunspot region currently visible on the Earth-facing side of the sun, along with a rolling 3-day forecast estimating the probability of significant flare activity from each one. These forecasts get revised multiple times a day as new imagery comes in from spacecraft like the Solar Dynamics Observatory, which captures the sun in multiple wavelengths of light, specifically chosen to highlight different layers of the solar atmosphere and different temperatures of plasma, allowing scientists to see the fine magnetic structure of an active region rather than just its visible surface appearance. When a flare does erupt, the X-ray radiation it produces reaches Earth in about 8 minutes, since light itself is the fastest thing traveling between the sun and our planet. And that radiation can cause immediate, short-lived disruptions to high-frequency radio communication on the sunlit side of Earth, even before any physical plasma has had time to arrive. It is only the follow-up coronal mass ejection, if the flare produces one, that carries the slower-moving cloud of charged particles capable of triggering the kind of sustained geomagnetic storm that affects power grids and satellites, and that cloud's 1 to 3 day transit time is exactly the window forecasters use to issue advanced storm watches once a coronagraph, an instrument specifically designed to block out the sun's overwhelming direct light in order to photograph the fainter plasma streaming outward from its edges, confirms that an eruption is indeed Earth-directed rather than heading off in some other direction entirely. That distinction between an Earth-directed eruption and one heading elsewhere matters enormously, because the sun is, from our perspective, a three-dimensional sphere, and a flare or CME only poses a direct threat if it happens to launch from a position on the solar disk that is actually aimed toward Earth's orbit. A sunspot region can be extraordinarily powerful and still pose comparatively little direct risk if it happens to be rotating along the edge of the visible disk rather than sitting closer to the center, since an eruption from the limb tends to send its plasma cloud off at an angle that largely misses our planet, even if it is spectacular to observe from a purely scientific standpoint. This is part of why solar physicists pay such close attention, not just to how magnetically complex a given region is, but to exactly where on the rotating disk it currently sits, and how many more days it has left facing Earth before the sun's own rotation, which completes roughly once every 27 days as observed from our vantage point, carries it around to the far side. An active region with a beta-delta classification that still has several days of Earth-facing time remaining carries meaningfully more near-term concern than an equally unstable region that is already rotating toward the limb and will be facing away from us within a day or two. There is also an important distinction worth drawing between the kind of aurora-producing storms that most people who follow space weather forecasts are hoping to see and the far rarer, genuinely extreme events that this new research is actually focused on. The May 2024 storm that produced widely photographed auroras across much of the United States, described earlier as the strongest in more than 2 decades, still fell well short of Carrington-level intensity. And it caused only intermittent, largely recoverable disruptions, rather than the kind of sustained continent-scale infrastructure damage that a true worst-case event could theoretically produce. That gap between a memorable but manageable storm and a genuinely catastrophic one is enormous, and it is precisely that upper tail of the probability distribution, the once-in-a-century and once-in-a-thousand-year events, sitting at the very extreme end, where this newly corrected research indicates the danger has been underestimated most severely. In other words, the vast majority of geomagnetic storms that occur in any given year, even the strong ones capable of producing dazzling aurora displays, are not the events this correction is primarily concerned with. It is specifically the rare outlier storms, the ones that occur perhaps once every few decades or less, where the corrected math suggests the difference between what forecasters assumed and what could actually happen is largest, And it is exactly those rare events that infrastructure planners, insurance risk modelers, and national security officials responsible for critical infrastructure resilience have spent the most effort trying to accurately estimate in the first place. That distinction also explains why this finding, despite sounding dramatic on the surface, has been received by the broader scientific community with a mixture of genuine concern and appropriate scientific caution rather than alarm. The authors of the Nature study are explicit that extremely large storms remain uncommon events by definition, which inherently limits how much real-world data exists to fully validate the corrected relationship at the very highest driving strengths. Confirming whether the doubled response genuinely holds at the most extreme end of the scale will likely require years of additional observation, ideally including data gathered during the next major storm that approaches or exceeds the intensity of the May 2024 event, when researchers can directly compare what the corrected model predicted against what Earth's magnetic field actually did in response. Scientific findings of this scale rarely settle a question permanently on their first publication, and the responsible next step, which researchers across the field are already discussing, involves stress testing the corrected relationship against additional historical storms and building improved instrumentation capable of reducing the very same single-point measurement uncertainty at L1 that caused the original saturation illusion in the first place. Some proposals under discussion include stationing additional monitoring spacecraft at different points along the solar wind's path toward Earth, which would allow forecasters to cross-reference multiple simultaneous readings rather than relying on a single spacecraft's necessarily incomplete view of a turbulent three-dimensional stream of plasma. For now, the practical reality is this. The specific week we are in carries a combination of factors: a magnetically unstable active region facing Earth, a solar cycle phase with a documented history of producing outlier extreme events, and a very recent example of a storm that outran its own forecast by a wide margin that together justify closer attention than an average week of the solar cycle would normally receive. It does not mean a Carrington-level catastrophe is about to strike. It means the people whose job is watching the sun for a living have good reason to be watching a little more closely than usual right now, and that the numbers they are using to judge how bad things could get, thanks to this newly corrected research, are finally starting to catch up with what the underlying physics has apparently been capable of producing all along. A quiet but genuinely significant shift in how seriously the rarest possible storm gets treated from this point forward. One final point worth carrying away from all of this is how ordinary the actual warning signs of a major storm tend to look in the days before they arrive. There is rarely a single dramatic siren moment. Instead, there's a sunspot region quietly rotating into view, a magnetic classification upgraded from beta to beta delta, and a routine daily bulletin, a chronograph image showing a faint plasma cloud expanding outward at an angle that happens to point toward Earth, and a forecast confidence level that shifts gradually upward over a series of otherwise unremarkable daily updates. That is precisely the kind of quiet, incremental buildup currently unfolding. And it is exactly why the researchers behind this correction, along with the forecasters applying it, are treating this stretch of days with the level of care that the newly understood physics actually calls for, rather than waiting for a dramatic headline moment that space weather, by its nature, rarely provides in advance.